Okay, I suppose we can start, and people are welcome to join in. So I welcome you to the live session, problem solving session, and live interaction for week 8. The topic of discussion today would be absolute and relative motion. Start in the lectures. Before that, I'll just briefly introduce myself. My name is Ganesh Ramaswamy. I'm a PhD scholar pursuing PhD under the guidance of Professor K. Ramesh and under the co-guidance of Professor U. Saronan from the Civil Engineering Department. And I welcome you to this session. So I would encourage you to solve the questions along with me and ask any questions that you have midway. Okay, so before we start, are there any questions from the sessions that we have discussed before? If there are any, you please bring them up. Otherwise, we can get started with the session today. Okay, I take it that there are no questions. So let us look at the first problem. Okay, a right angled slotted arm. So it's a slotted arm, and it is given that it is a right angled slotted arm with pins A and B are constrained to move in the slots as shown. So we are able to see that here we have a vertical slot and here we have a horizontal slot for the pins to move. So for the velocity of pin A to be as marked, that is the velocity is shown that it is in the upward pointing direction, VA. Which of the following is the correct expression for the magnitude of the velocity of pin B is what is asked. So this and we are given 4 options. So let us see how to go about it. So basically absolute motion deals with systems where there are constraints available for us to exploit using geometry, and then based on subsequent differentiation we will be able to get the velocities and accelerations, so to speak. So basically the idea is to relate the quantities first using some constraints of the system based on geometry, and appropriately differentiate systematically and substitute for the values. So if we see here, from here we are able to see that this tan theta is nothing but HA by XA, A, capital A. Okay, so if we were to say, if we were to differentiate this, so we can see that tan theta is nothing but HA by XA. So if we differentiated this, what will we get? We'll get secant squared theta into theta dot, which will be XA into HA dot minus HA into XA dot by XA the whole squared. Okay, but we can see that the slot is fixed at one position. So the slot is not moving, only the pin is moving along the slot. So essentially we can see that HA is the only variable here. XA is fixed. So its differentiation of that will be 0. That is the essence here. So if I were to write this, secant squared theta is nothing but XA dot is 0. So this goes to 0. So we get nothing but HA dot by XA. But from the geometry, HA dot is nothing but VA. That is what we have been given. So this is essentially VA by XA. So far so good. So this theta dot we can get as VA by XA secant squared theta. Okay. Now we can also see here that if this is theta, then this angle would be 90 minus theta, or pi by 2 minus theta, whatever it is. So since this is also given as a right angle, this also becomes theta. So from that relation again we can write that tan theta is nothing but xb by hb, but tan theta is nothing but xb by hb. So we differentiate it again similarly. So we get theta dot secant squared theta is equal to, now we have to note that here HP is fixed because that's a horizontal slot. It is not moving in space. XB is the distance of this from this point to the pin B. So that is the essentially that is the variable here, and this quantity is fixed. So its derivative also will be fixed. So this will, I'll spare you the details. It will come out to nothing but xb dot by hb, which is nothing but vb by hb. Okay, so again theta dot, from here we can see that vb by hb secant squared theta. So equating the two, we can see that vb is vb by hb secant squared theta is va by xa secant squared theta. So vb will come out to be hb by xa into va hb hb. So these two can't be the options because they have xb on the numerator. Hb by xa into va. So our answer is B. So we have it is a simple problem. Just to illustrate that from the constraints of the system, we have to write relating the kinematical quantities and then subsequently differentiate them to get our velocities and accelerations. So if there are any questions on this, I'll take them now. Otherwise, we will move on to the next problem. Understandably, this is a simple problem, but it is good that we get some practice with the simpler ones so that we are able to identify the concepts clearly, what is to be applied. Okay. So are there any questions? Okay. So yes. Okay. All right. Thank you, Amandeep, for clarifying. So we'll move to the next problem. So just to keep it a little more interactive, I would urge that we will just take a small poll on this as to what you think. So let me read the question out. A person looks at the paths traced by two arbitrary points on a rigid body. So this is a rigid body. This is the rigid body that we are talking about. And then we have 2 points, 1 and 2. And the person observes that both the paths are congruent circles at some time t. So when the person sees it, it makes a movement like that, and he is able to see, he has just in the mind traced the path of both the points, and it comes out as circles, congruent circles, that is of equal radius. So the rigid body can be said to be having which type of motion here, whether it is having rectilinear translation, general plane motion, curvilinear translation, or fixed axis rotation. So I'll just create a poll so you guys can just. So I hope you're able to see the poll. If you could just, this is the question. So what is the path that the rigid body is? The paths are given. What is the type of motion undergone by the rigid body? Okay, we have one answer. All right. Fixed. Okay. D. Okay. All right. So I'll stop the poll now, and perhaps we can discuss this further. So all right. So I've got all sorts of answers. So the thing here is only the answer which is correct has not come out in the poll. So let me clarify that a little bit. So see, for a rigid body, if we take any 2 points and we are able to see its velocity, determine the velocity of 2 points on a rigid body, then the entire motion of that body is known. So some minimum of 2 points are required to characterize this thing. So if we see here itself, we can see that velocity at this point is like that, and velocity is like that here. So throughout, if we see, the velocities are parallel. So essentially, if the two velocity vectors are parallel and equal, the body is undergoing translation only. So it is not undergoing rotation. That is clear. Actually, I have drawn it a little bigger. Perhaps I should have taken the same measure here. So let me just do that. So it will be equal. Okay. So it is not a case of rotation. If it is not a case of rotation, automatically it cannot be general plane motion, because general plane motion includes rotation as one of its components along with translation. Okay, so we can see that B cannot be the answer. D is not the answer, B is not the answer. Rectilinear translation or curvilinear translation. We are able to see that the path trace by the 2 points is a circle. It's a curve. It's not a line, straight line. It is having a change of slope. So it is nothing but curvilinear translation. So the answer to this question is essentially curvilinear translation. So it is important to understand that the body is moving like that. So if I were to just sketch this body here, okay. So let me just rotate it. So the body is moving like that. I hope you're able to see it in the screen. So this is the kind of motion that the body is having. So if it went here and it had rotated like that, then it would have been general plane motion. Since that is not the case, neither it is moving like that. It is not rectilinear translation because it is not moving in a straight line. It is moving in a circular path is what is given. Fixed axis rotation would have been some point on this is fixed and it is having rotation about that point. That is, it's a little hard for me to show, but essentially one point is fixed in space and it is rotating about that. So that is also not the case here because we are able to see that both the points are displaced from their original position. So the motion that is undergone by the body is like that. So that is nothing but curvilinear translation. So that is the correct answer to this question. So are there any questions here? I'm happy to take any questions if there are. Okay, I take it that it is clear. So basically, even while attempting the assignments and exam questions, it is essential to quickly see. Uh, First, what you could do is you could just take a look at if there are paths given, you can just take a look if they are congruent or if they are concentric with a common center. So all this will help you identify whether it is what kind of motion it is having, and accordingly you can perhaps reduce your calculation. But nonetheless, once you understand this motion correctly, you will be able to write the kinetic equations and the kinematic equations. One thing is essential to understand is in the case of kinetics, the topic of week 11, we will be seeing that first is it is essential to identify the nature of the motion that the body is taking place. That is why these type of questions, what the rigid body is undergoing, which type of motion, this you will see numerous times in the assignments. The reason behind that is that once we become conversant and comfortable with identifying the type of motion, we will quickly because kinetics is based on dividing the motion into buckets. Basically, if it falls within one bucket of general plane motion, we have some equations. In general, everything is general plane motion and the other things can be considered as special categories, special cases of that. But just to quickly solve the questions, it is helpful that we identify the type of motion a priori and then apply the kinetic equations so that we are able to solve the questions quickly. Okay, so I hope this is clear. So this is a interesting question that brought about something. So, uh, so just to have one more uh, this thing, we'll have one more poll just to make it a little interactive. But let me read out the question first and let me tell you what they are expecting. In order to decompose general plane motion of a rigid body into a translation and a rotation, we have seen that a generalized force system consists of a force and a equivalent couple. Sometimes the couple might be absent, sometimes the force might be absent, sometimes both might be present. So when both are present, essentially sum total of the force leads to a translation and sum total of the moments leads to a rotation. When both simultaneously exist, the body undergoes general plane motion. So the effects are what we are trying to decompose here and study. So in order to decompose general plane motion of a rigid body into a rotation and a translation, one writes the position vector. So the position vector of this RB, this point RB is written as with respect to O he has written. Since O is the origin, we generally omit writing RB with respect to O. It is understood that we are writing it with respect to the origin. That is the easy convention that has been followed here. Okay, so it is, sorry, it is given that RB, the person has written that it is RA plus RER. So Ra is a vector. That is why the unit vectors have not been mentioned here. For this Ra, if you see, it doesn't say I cap, j cap because they have represented as a vector. But if we were to actually write it in component form, we will be writing it as in the vector scalar components only, so that we can differentiate them accordingly. So this was differentiated. One writes the position vector and gets the velocity. What is velocity? We know that velocity is nothing but the time rate of change of the position, right? So if we if we systematically differentiate this, it will be Ra dot plus RER, R dot ER plus RER dot, right? So not to confuse, see here ER, whenever we write E, the general convention is it is considered to be a unit vector. So this is similar to E or cap. So not to be confused as it is some other vector altogether. It is a vector of unit of a magnitude 1. Okay, so I'll just move this here. Move this here. And then what did we get? Ra vector. Ra vector is the position vector of A with respect to O. And its differentiation will be nothing but VA. It is a velocity of A. Plus R dot ER plus, we have seen in the last class that ER dot is nothing but theta dot E theta. This we have seen in the last class, last session, if you remember. We wrote ER and E theta in terms of EX and EY with cos theta, sin theta components, and then we differentiated them systematically. And out came the result that ER dot is nothing but theta dot ER dot is nothing but theta dot E theta, and E theta dot is minus theta dot ER. I hope you remember. And those session videos have also been uploaded, and the slides are also available on that on the page if you see. So in case you haven't been able to access it, it is available now. In case you want to see it. Okay, so we will just take here. It will be ER theta dot E theta. So now the person gets a velocity of B. The person gets this expression after deducing all the physics. It is getting this expression. So what he is essentially getting is VA plus R theta dot ER, E theta is what is getting. So what it implies is this component is going to 0. This component is going to 0. So when will that go to 0? When R is constant. So based on that, which of the following is a necessary condition for this step to be correct? For this step to be correct, R dot must be constant. Based on that, can we make some deductions here? What are the options? Point B is a point on the rigid body, and point A can be taken anywhere in space. Or point A is a point on the rigid body and point B can be taken anywhere in space. One or the two. Or point A and B can be taken anywhere in space and this will always hold. Or points A and B both have to be taken necessarily on the rigid body, but we at arbitrary locations. It need not be at fixed points on the rigid body, but at arbitrary locations. So could we just have a poll on this if you people are interested? So which one do you think is right here? You can just select based on the discussions that we have had. I made the poll live. You can just take which one do you think is correct? Okay. Okay. So I've got some answers. Okay, I'll end this poll. Let me just clarify. So the answers which I have got include A, B, and D. So let me clarify as to why these only one out of them is correct. Actually, the correct answer is D, because we are saying that points A and B can be taken anywhere on the rigid body. What is the definition of a rigid body? That two arbitrary points taken on that rigid body, the distance between them remains fixed. If I were to consider it like this, let me just move it here. And here we had a dot. Okay. So if I consider a body like that, if that is my rigid body, then r dot is 0 because r is a fixed quantity. It doesn't undergo any deformation. So that rigid body, r subsumes that rigid body, which is why points A and B can be taken anywhere on that rigid body itself. If we were to say that point A is correct, that is point B is taken on the rigid body, let us say, and point A can be taken anywhere in space. So essentially we are cutting out this portion. We are saying that that is taken on the rigid body. Let us say that is the rigid body, the pink portion, and this is outside. So this distance need not be constant. As long as the rigid body domain is there, the distance is constant is what we know. If there is no material in that space, then we cannot say anything about it, which is why A and B cannot be correct answers, which are necessary for this condition to hold. That is why these have to be taken necessarily on the rigid body. And this, yes, yeah, about which axis? Okay, okay, yeah. So in that case also you are taking A on A can be anywhere on the body, right? No, that is only when it is undergoing this thing, right? It is not undergoing general plane motion. No, it is undergoing a fixed axis rotation about some point, right? No, this theta dot which we are saying is the angular velocity of that rigid body, is what we are trying to analyze. So in that case, how will you conclude that theta dot is the angular velocity of the rigid body, right? So what we are essentially trying to do here is a body in space, it is having some kind of motion. We are trying to study that motion into by decomposing it into two parts. How we can decompose? Once we know a point on that rigid body, we know its motion, and then with respect to this, the other point can only have circular motion. That is the constraint here. It will only have a circular motion if the distance between these 2 points are fixed. Then VA, if we move VA, then we know how VB will move. VA is moving. We sit at VA and we sit at A and look at B. So we ourselves are having a velocity, and in addition to that, the point B will appear to rotate about us, the observer sitting at A. This is how we are trying to decompose. So that theta dot is essentially the angular velocity of the body, of the rigid body under question. Okay, yeah, all right. Okay, then. So this is basically the essence of our relative motion. So we know by the constraint of the system, we will know at least one point what kind of velocity or movement it is having. Then with respect to that, some other point we will take. We will just differentiate. If we differentiate this again, we will get acceleration of B, this acceleration of A, and then the differentiation of this term, which is a little bit involved. We will see when we get to accelerations, we will see it will again have two components. One will be alpha, one will be theta double dot. Why don't we differentiate that now itself and see? So AB, we VA dot is nothing but AA dot plus R dot theta dot R dot theta dot E theta plus R theta double dot E theta plus R theta dot E theta dot. Now again this will go to 0. This will be say same R theta double dot, which is nothing but our centripetal acceleration. So and this component will come out as R, it will come out as minus R theta dot squared E R. Sorry, this component is the centripetal acceleration, that is R cross alpha, because theta double dot is nothing but alpha. So that is the tangential acceleration. Sorry, I mixed the two up, but I hope that is clear what I meant to say. So this is the essence we are trying to exploit in our relative motion analysis, and this will become clear if we see a couple of problems. It's not what we need to keep in mind is we need to differentiate them systematically. Once we get the expressions, it is very trivial to substitute for them and get it. But before that, we'll just see a couple of things. Okay, we'll see that after this question. So let us have a look at this question. A side view of a large window OP, OP is the window, is shown, is being opened using a hydraulic cylinder CD. CD is the hydraulic cylinder here. This is the hydraulic cylinder as shown in the figure. The hydraulic cylinder extends at a constant rate. So it is given that this is extending. So essentially it is trying to open the window. It is extending at a constant rate of 0.7 meters per second. So what this is saying is this S is increasing with 0.7 meters per second velocity at the rate of 0.7 meters per second. Neglect any frictional effects, and when theta equal to 45 degrees, when this theta is 45 degrees, you arrive at some of the quantities that are asked. So the length of the hydraulic arm S, what is this length? When this is 45 degrees, what will be this length is what is asked at this given instant. And then we are supposed to calculate angular velocity of the window in radians per second, which is nothing but this is S is what we have been asked. Here, angular velocity of the window is nothing but theta dot. Angular acceleration of the window is theta double dot. So essentially these three quantities we have been asked to calculate. So let us see how to go about this. So as I had mentioned in the starting classes that it is better we brush up our fundamentals on sine rule and cosine rule. So if we see using cosine rule, we can simply write this as s squared. If we were to consider this triangle, if we consider this triangle, so that will come out to be 2.5 squared plus 0.75 squared minus 2.5 minus 2 into 2.5 into 0.75 cos theta. So this comes directly from our cosine rule. So the square of the sum minus 2 into the lengths of the sum into cos theta gives us the square of the third arm when we consider a triangle. This is applicable when it is not a right triangle, we can use this. If it is a right triangle, we will see that cos theta, theta is pi by 2, cos theta is 0. So it comes to our Pythagoras theorem. Simply root over square of the sides comes to a square. So this is the more general term. So, okay. So at theta equal to 45 degrees, it is given. So we can simply calculate that once. What is s square? 2.5 square plus 0.75 square minus 2 into 2.5 into 0.75 into cos 45. So it comes to 0.41. So 1 minute, 2.5 squared plus so S, sorry, S comes out to be 2.04 meters. If we calculate this, so S is 2.04 meters. Okay, I'll just add a page here. Okay, so we had this S squared is 2.5 squared plus 0.75 squared minus 2 into 2.5 into 0.75 is nothing but 3.75 cos theta. This is the constraint given from the question itself. We have this. So it is just like the first problem that we solved. Once we have a constraint, we subsequently systematically differentiate them and get the kinematical quantities. So let us differentiate it. So it will come to 2s. Yes. Yeah. S by how? It is not a right triangle, right? Yeah, yeah. Maybe see at the in the question, if it is given that it is 45 degrees, at some point it might turn out if this was also 0.75, then it could have happened that maybe it comes to a right triangle. But we should, it is advisable that we go by the general. Okay, okay, but the figure, yes, yes. So that is also, it's a good point that you brought that up. So one thing we should keep in mind is sometimes to confuse also, people will give some sort of a diagram. So please don't go by the diagram, go by the values. I am, because this does look like 90 degrees, so it is an understandable this thing. Okay, so, okay then. So we'll proceed with this. So this comes to minus 3.75 theta dot sine theta, if we differentiate, because other quantities are constants and they don't change, so their differentiation is 0. So what have we been asked here? The angular velocity of the window in radians per second is what we have been asked. That is theta dot is what we have been asked. So we can easily calculate theta dot from here. 2s s theta by 3.75 cos sine theta. Sorry, sine theta. Do we know all the quantities here? S we just calculated. S dot, do we know? It has been given in the question that it is increasing, extending at a constant rate of 0.7. So S dot is essentially 0.7. This is nothing but S dot. And it is qualified that it is constant. So what does that imply? This implies that S double dot is 0. It is constantly increasing, extending. We will see where we apply that. So 2 into what is S that we got 2.04 into S dot is 0.7 given, divided by 3.75 into what is that, theta is 45 degrees, so it will be 0.7. I'll just write it 1 by root 2 just for convenience. So what will this come out to be? We can calculate this. This comes out as 1.07 radians per second. Okay, so far so good. We can see here that when S increases, theta also increases from the geometry, how it has been defined. So it is positive. It makes sense that it is positive. Okay, let us write this equation again. Let me copy this equation again. Next, we need the angular acceleration. This is a simple problem because all the constraints are well defined and we are able to use absolute motion. In many cases, it might not be so, where we will resort to relative motion, which we will see in the subsequent example. Let us differentiate this again systematically. Differentiating again, what will we get? 2s s double dot plus 2s dot squared is equal to 3.75 theta double dot sine theta plus 3.75 theta dot squared cos theta. This is what we will get if we apply the product rule properly. What is the quantity that we want from here? Theta double dot. So let us solve for theta double dot as a general expression here. We will get 2s s double dot plus 2s dot squared divided by, sorry, minus 3.75 theta dot squared cos theta. All of this divided by 3.75 sine theta. So calculating the quantities is quite easy, as we just have to ensure that we are doing the differentiation systematically. From the question, we know that this is 0. So we have only other two quantities to account for. So what will that be? 2 into s dot. S dot, do we know? It is given 0.7 squared minus 3.75 into theta dot, we just found out as 1.07 squared. Cos 45 is 1 by root 2. So I'll just write root by root 2 here. 3.75 by root 2. What does this come out to be? Into 0.7 squared. So it comes out to 0.78. I urge you to solve it along and then point out if there are any calculations. I hope not. Radians per second squared. I'll just verify it once again. Yeah, so minus 0.78 radians per second squared is what I'm getting. So it should be noted that theta dot, if it is positive, theta double dot needn't be always positive. We cannot say anything about theta double dot essentially. Accelerations are a tricky quantity which we should always derive and then assign, let the mathematics assign the sign to it, because many times people might have a misconception that if angular velocity is positive and increasing, it automatically, it's a general notion that they take angular acceleration also to be positive, which is not so, which is brought out clearly here. So 1.07 radians per second, not second squared, radians per second is what we got. And theta double dot we got as 0.78 radians per second squared. So we are able to see if we were to, let us say, have an assembly that has to, if we were to build something like this, we know at what speed this should operate so that accelerations are under control. So that, for example, even in the lectures, it is discussed that while they're designing joy rides and all that, in theme parks, we should know what is the acceleration that the person who is sitting in that would be facing. That should be within some limits so that it doesn't affect their health. So for all those things, we are able to see that we are nicely extending those concepts one after the other, introducing little more complexity so that we are able to analyze systems which have multiple components such as this. So if there are any questions here, I'm happy to take them now. Otherwise, we'll move on to the last problem that we have for the day. It's a little big, but yeah, before that, if there are any questions, I'm happy to take them. Yeah. Like, yeah, that is on this, there is some body. Okay. Yeah. No, as long as it is stuck. Yeah. Yes. Please go ahead. Yeah. Yeah. Yes. If it is on this plane, it will be a general plane motion. Only thing is the quantity about which it is rolling or whatever, so to speak, that also is having an acceleration. If, okay, okay, it is sliding about some point, let us say. We will be given some constraints, right, as to how it is sliding. Okay, yeah. So its velocity at every point will change with respect to the observer, right? So at every point, let us say this is the point where it is at this moment, at some instant. So since it is changing at every instant, we have to define the instant where we want to analyze it, right? So we know theta dot. We know, let us say it is at point D at this instant, it is here. So can we get the velocity of this point based on theta dot and the distance from the pivot? We'll be able to get that. So it is just a matter of adding the vectors in order to get it. Okay. Yeah. Yeah. So this is what we are essentially doing. What we are doing is we are decomposing that into several components, analyzing the subsystems one after the other, and then adding them together in order to get the net effect. So yeah, that's a good question. So I'll just repeat what the question was. If suppose if this window, there was an object sliding over this window, if we were to analyze its motion and get its kinematical quantities, how will we go about doing that? Since it is changing at every instant, essentially dynamics deals with calculating quantities at some particular instant of time. And then if we keep that instant as a variable, we will be able to see the time response of that system, how with varying time how it behaves, based on which we will select some cutoff point. Maybe at this point, it after so much of time, its acceleration becomes that much if it is monotonically increasing. So we will cut our time interval to this, after which some reversal of motion will take place. Something to that effect will happen. So essentially, at every instant, we should know how to analyze that. Once we analyze at an instant, it is easy for us to calculate what will happen with time. If let us say this theta dot, if this theta double dot didn't exist, then theta dot will be constant. So it is having a same motion with time, constant motion with time. So we are able to calculate what is the angular velocity of any point. What is the linear velocity of any point. So anything that is in contact with that will also have that linear velocity. That is the constraint here. Based on its velocity, which we know, and the linear velocity of the point on which it is sitting, we can do vector sum and get its sum total of the absolute motion that it is having. So that is the essence here with which we proceed and decompose the components. Okay, so with that, let us move to the next question. That's a good question you asked. Okay, so a weight, this is the weight. A weight is suspended on a pivoted disk moving in the direction as shown with a constant velocity v equal to 0.4 in the direction shown. Okay, so this is moving down with 0.4 meters per second. This is wrapped around the disk and it is rotating. That is given. A pin on the periphery of this disk, so we have that disk, and then a pin is connected to a rigid link. So we have a rigid link here. It is connected to that, and the other end of the rigid link is connected to a slider. We have that slider here. Slider meaning it is constrained to move in those guides. If we see our roller supports also, sometimes we will have a guided roller support. It will look like that. So there will be rollers inside that. Why that is done, this is just a representation. Why that is done is it won't allow you to lift off also. So it will offer reactions in both the directions. So such a constraint is given that VB can move only along that direction. And its directions are given. 60 degrees the inclination of that slot. Okay. Whose other end is connected to the slider box. Considering the positive coordinate directions as shown. So this is the positive coordinate direction shown. X, Y. So why this is given? So that we know that Z is pointing out of the plane of the paper. If this be the case, then our anti-clockwise rotations would be positive. So these will be positive and these will be negative. Because its axis, if you see from the right hand rule, its axis aligns with the positive Z axis. That is why this has been given. Okay. So answer the following question at the instant considered. At this instant, the configuration of the system is such. That means this is vertical, this is perfectly horizontal, and then we have that thing connected over here. Okay, when the rigid link is horizontal. So this is given to be horizontal and this is connected to that. So we have been asked some quantities. Let us see what they are. So the magnitude of velocity of the pin at A in meters per second is what is asked. So from here, this disk, we are able to see that the velocity of this point is 0.4 meters per second. And this is connected totally, it's a pivot disk, it's a single unit. So it can have only one angular velocity. So 0.4 is given. What is the distance from its center? It is this 0.7 by 2 because that is the diameter. So this is the 0.7 by 2. So its angular velocity will come out to be 8 by 7. So omega of the disk is this disk. Omega of this pivoted disk is nothing but 8 by 7 k cap minus k cap. Let me write it in the vector form itself. Okay, so it is minus k cap because it is rotating in the clockwise direction as we have seen. So what is the velocity of A is what is asked. We can simply take the product and conclude what it is, but I would like to emphasize a little bit on dot and cross product so that not dot and cross products when we have two quantities and when we have a single quantity. So let me just show that. So velocity of point A will be velocity of point O. I think it is called O. Yeah, this pivot is called O. So it will be velocity of O plus omega of the disk cross r of A with respect to O. This is what we will be using time and again for velocity. Similarly, acceleration we will subsequently see. We are able to see that there is no velocity for this O. It is a fixed pivot. So essentially our VA comes out to be, what is omega of the disk? We know it is 8 by 7 k cap minus 8 by 7 k cap crossed with R A with respect to O. We are able to see it is 0.6 is the distance here. So it is 0.6 j cap. And then if we do this, so we know if we go like that, it will be positive. If we have a product going that way, it will be negative. So k cross j is minus I. So it will be minus minus plus 8.7 into 0.6 I cap is what we will get. And even from the physics, we can see if it is rotating like that, point A will be moving to the right, which is in the positive x direction, which is consistent with what we are getting here. So what will that velocity be? 0.6 into 8 by 7. So it is 0.68. 0.68 is what we are getting here. Okay. Velocity of A is 0.685 I cap. Yeah. So this we have been able to arrive at. And mind you, the magnitude is asked. So although it's a positive quantity, doesn't matter. But if it were negative, we are supposed to report the magnitude. We are supposed to keep note of that. Okay. The total magnitude or total acceleration of point A in meters per second square. So the next step logically is that only. So velocity of A we saw as velocity of O plus omega disk crossed with R A with respect to O. Right. So similarly, acceleration of A, if we see, it will come out as acceleration of O plus omega cross disk, omega cross R plus alpha disk cross R. So one is pointing towards the center, one is tangential. So what is alpha? So we know that any point in circular motion, we know that any point, if it is having tangential acceleration, if this is R, if this is having A acceleration, tangential acceleration AT, then our alpha is nothing but AT by R. So we have been told that this weight is moving with a constant velocity. So our acceleration of the disk is essentially 0. So this is 0. What else is 0? AO is fixed. It is a fixed pivot. So we are essentially dealing with only one quantity here. Acceleration of A is nothing but minus 8 by 7 k cap cross minus 8 by 7 k cap crossed, or that we saw it was 0.6 j cap. So when we take cross products of like consecutively, when we take cross products, it is nothing but negative of the product, and then we retain the unit vector there. So this j will again get replicated here when we do double cross products, and then it will be the, yeah, so it will be, one minute, it will be the product of these quantities. For quick calculation, you can do that. So it is minus 8 by 7 squared into 0.6. Negative of that. So it comes out to minus 0.78 j cap. So acceleration of A comes to minus 0.78 j cap. It is vector triple product, but it is better to introduce it from the first principles because some might not be familiar with the terminology. So even for those, I'm avoiding using the terminology like that, and I'm just saying when we do double cross products, what is coming out. It has been okay, okay, all right, very good. Okay, so the magnitude of the total acceleration is 0.78 meters per second squared. Pointing, it is negative. So we know that when it is having circular motion, there is no tangential acceleration. Nonetheless, there will be a centripetal acceleration pulling it towards it, which is what is changing the direction. So that is what this 0.78 is about. Okay, so what is the next quantity that we have to calculate? Let us see. The magnitude of the velocity of the slider block in meters per second. This slider block that we have, its magnitude of velocity is asked. From the fact that it is constrained to move along the slide, along that along that slot, its velocity and accelerations are constrained by the system. If this were a curved slot, then it will have two components of acceleration, which will also be responsible for the change in the direction. Since it's a linear slot, acceleration and velocity can only be along this direction. So essentially, unit, we know the unit vectors. Uh, at least we know which direction it is going to go. We only don't know the magnitude. Okay, so let us presume that it it has velocity and accelerations going that way. Okay, so do we know the unit vector in that direction? We know it will come out as cos theta I plus sin theta j, where n is along the slot. So it is given that theta is 60 degrees. So n is cos 60 I plus root 3 by 2, 0.86 j, 866 j. This we know. Okay. So what will velocity of what is the slider block do? We have identified with with B. So let us say B. Velocity of B is nothing but velocity magnitude n cap. So it is VB 0.5 VB I cap plus 0.866 VB J cap. But VB is not known as of now. Similarly, acceleration of B will be 0.5 AB I cap plus 0.866 AB J cap. Both are unknown for now. Okay. So we have to calculate that. That is what we have to do. Now, what other constraints are given in the system? We know that this is a rigid link. So, and we know one end of it is point A. And we know the quantities, acceleration and velocity of point A. So, can we calculate acceleration or velocity of point B? Because this is rigid, we can. We can do that using our relative motion analysis. So, what is VB from the link? VB is velocity of A plus omega link cross R B with respect to A. This is also unknown for now. Let us assume that omega link is vector is omega link k cap. Let us assume it is rotating like that. Okay, so let me just add a couple of pages here. So velocity of B, we know this is the quantity here. It's nothing but velocity of A. Do we know velocity of A? We calculated as 0.685 I plus omega link. Let us say k cap. Let me put this here so that there is space. Crossed with what is RB with respect to A? We are able to see that it is horizontal. So it is 3.8 I. So essentially we just have to do the cross product and group the similar terms. So 0.5 VB I cap plus 0.866 VB J cap is equal to K cross I is J. So it is 0.685 I plus 3.8 omega link J cap. Can we group these quantities? These have to be equal for this equation to hold. So from here we can see that VB is nothing but 0.685 by 0.5, 1.37 meters per second, and 0.866 VB by 3.8 is our omega link, which comes out as 1 point into root 3 by 2 by 3.8, which comes to 0.312 radians per second. So it is coming out as positive. So whatever direction we took is correct. It is that way only. So we have got these quantities also now. Omega link also we have got. So let us fill that up. 1.37. What is the magnitude is 1.37 meters per second. The magnitude of angular velocity of the link we have just got. What was that? 0.312 radians per second squared. So the magnitude of acceleration of the block is asked now. We can do a similar exercise. We have the expression here. Just copy that. Let me do it in the next page. Okay, this is nothing but our acceleration of A plus omega link cross cross RB with respect to A plus alpha link cross RB with respect to A. We don't know anything about alpha link. We had concluded that alpha disk is 0 because it had constant velocity at that point because of the constraints of the system. We don't know anything about alpha link. So we will just take it similar to our omega, we will take it as alpha k cap. So take alpha link as alpha link k cap. Okay. So if we were to write this AB I cap plus 0.866 AB J. What is acceleration of A? We got it here as minus 0.78 J. And omega link we have got just in the last slide. It is 0.312 K cap cross 3.8 I. RB with respect to A is 3.8 I plus alpha link K cap crossed with 3.8 I. So now it is just a matter of calculating these quantities. 6 AB J is equal to what are the things that will give J? K cross I is J. So these two essentially will give me J components. So why don't I write them together? Minus 0.78. K cross I is positive J. So plus 3.8 alpha link. This is I minus 0.312 squared into 3.8 I. Sorry, J. Yes. Sorry. Thank you. Thank you for the correction. So that is J and this is I. So again, it is just a matter of comparing it. So from here, we can directly compare these two. These two we can compare and then pick some other color. These two will be equal. From those, we can get the unknown quantities. What does it come out as? Into 3.8 by zero point 0.5 is minus 0.74 meters per second squared is what we get. And our alpha link would be this quantity into 0. Although not asked, but still let us just calculate it as 0.78 by 3.8. I hope I am correct. I'll just check it once again. 0.4 radians per second squared. Minus 0.78 plus 3.8 into. Yeah. So 0.0366, which is 0.04. Okay, so acceleration we have got. This quantity was not asked, but it is just a natural extension of the problem. One could just as easily ask that. So AB we have got here. This is our final quantity. AB is minus 0.74. So the magnitude is asked 0.74 meters per second squared. So this is what is this analysis about. So and we have got all the quantities now. So if there are any questions on the way we have solved or anything related to that, I'm happy to take them now. This ends the problems that I wanted to discuss today on relative motion and absolute motion. Next week we will be seeing relative motion in more detail with little more some more good problems. Yes, doubt in truss analysis. Yes, please go ahead. I am readily not remembering which problem it is, but I'll surely address it. See, the thing is, stability m plus r equal to 2j is a minimum requirement for us to keep it in equilibrium. But m arrangement of m is not captured in that equation. M could be arranged, members could be arranged in any way. So if we have to take a simple truss like that, and then I have another this thing like that. So if we see, even if okay, I'll just reduce it by 1. Okay, so this also, if you see, m plus r equal to 2j will hold, but this will not be stable. Why? Let us say I cut a section here. Okay, this will be supported like that. So if I were to draw the free body diagram, I have reactions like that, and presumably a horizontal reaction. If there are no horizontal forces, there won't be any horizontal reaction. So if I take a section like that, what I'm essentially doing is I'm not balancing the shear. Let me take a section and let us consider the right side portion of it. So I will just erase this here. This is what I have considered. Okay, here there will be that member force and all that. That's fine. But I'm having both the forces. We know that trusses are axial, truss members are axial members, which carry only axial forces. So all the forces are pointing like this. So will this be in equilibrium? If we do sigma, let us say this is some RB, if this was B, sigma Fy equal to 0, RB plus there is nothing to balance it, right? So essentially this doesn't hold. There is nothing making RB to counter RB and make the acceleration 0. So this will not be 0. So this will be some mass times some acceleration will come in here because it is not being balanced. So we cannot blindly say that m plus r equal to 2j if that is satisfied. It is holding the stability condition also. It is necessary, but it is not sufficient because we have to look at the arrangements also. Yeah, 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 yeah. That is what is that instability is all about. Yes, it's not stable. Yeah, that was the question. No, that was the question. They asked that. See here, m plus r equal to 2j will hold. M plus r would be equal to 2j, but it is still not stable. Why? Because this is not being balanced. So we need to threadbare analyze it, see if the members are arranged properly in order to conclude something on stability. Is it clear? Is, yeah. Okay. Okay. Thank you. All right. So it's good that some questions are coming up. So are there any other questions that that are there? I'm happy to take them now. I hope these sessions are helping you out in some way, one way or the other. So if there are any feedbacks on what kind of problems I should solve or regarding my delivery, I welcome them. You can give it. And I understand that they have also circulated a feedback form for these sessions. So please feel free to record your honest feedback about these sessions. If they are constructive, I'm more than happy to incorporate those comments so that the subsequent sessions address any shortcomings that are there that you notice. So I urge you to give the feedback. I don't urge you to give a positive feedback. I urge you to give an honest feedback about what you feel. If there are any shortcomings, I'll try to address them so that this initiative that has been started is taken to its logical conclusion. That logical conclusion being that it is helpful for the students that are attending it. So thank you for attending this session. I hope to see you in the next session on next Friday, 6 o'clock. And if meanwhile, if there are any questions, please feel free to ask them in the forum. Thank you. Thank you for attending.